The next episode of the AV Experience. I'm your host, Ryan Charpentier, and we're joined by the beautiful Ben Goff, but the even more beautiful Peter Aylett, because the hair really gets me. And if you had the glasses where I could see my own reflection, it would take it even further. It's like one of those birds that can't pick up on itself, and I think I was seeing something. Never mind. How have you guys been?
Good. Yeah.
You are 6 hours ahead of me. It's 2 p.m. or is it 1 p.m.?
Only 5 at the moment because our daylight savings don't quite coordinate.
Isn't that dumb? Like, daylight savings in and of itself is dumb, and then we don't make them match, and it's
well, it's
awful.
like we don't make our languages match either. I speak English, you don't.
I'm a barbarian.
Not quite, but
borderline.
It's certainly not English.
Borderline.
We can accept the language. We can't accept the freedom units.
No.
Engineering is done in metric. Not
but you guys use some freedom units in some stuff, which is bizarre. You use both.
Sure. Not for engineering.
We are just dumb, and we embrace the dumbness. You guys are sometimes dumb, sometimes not.
No, we are the worst, because at least you're consistent and most of the rest of the world is consistent. We're just not consistent. So engineering, it's metric, but when it comes to beer, that's freedom units. Apart from the fact that your 1 pint is 16 ounces, I believe. Our full pint is 20 ounces.
Well, you're better than us for that exact reason. No, that exact reason. Your pint is bigger.
Here's the worst thing. If you go and buy milk cow, comes in pints. If you buy pretend milk from an almond, comes in litres. Yep.
Why does it come in pints?
Because the farming industry won't
free,
change
obviously.
it.
Oh.
The farming industry are very set in their ways, but the soy, almond, coconut, etc. Different milk types.
We're going to have to address Ben's internet at some point. So it's not just me.
It's not just you. It's Ben's internet where he is. It's a bit, I'm going to use an English word here. Shit.
That's fair. That is fair. So Ben brought up the topic. I don't remember if you did this online or offline or both, Ben, but you made the suggestion or kind of hinted that Peter had a formula, Aylett ratio, that you guys like. Not saying it's an industry thing, but that you guys like. Does not mean that everybody is going to like it. But last week we talked about sub placement,
right,
and things that you could do. And now I think this is a good way to synergize or to go off of that to talk about how much. Right, you got placement.
Yeah. We got a question a couple of weeks back, and I very much bailed out on answering it. There was a question even before we did the placement on how much sub is going to be enough, because we've joked pretty much every episode we've done so far that if you think you have enough subs, you're wrong. So, and we've alluded to this, and someone asked, well, how much is enough? So I immediately said, we'll get Peter on. So we do have a spreadsheet that Peter is currently the master of. I think we will talk about the Aylett ratio, and this is one of those great things where when you work on something, it's other people's prerogative to name it. We have a very small WhatsApp group of some of the finest cinema engineers in the world, let's be honest. And while bouncing these ideas around, we called it the Aylett ratio. So Peter's not done that himself. We've named it in his honor. But we need him here to talk about it. I wasn't going to run that through when this has been Peter's baby somewhat. So we need him here to bring it straight direct from Peter's mouth.
Well, to start this off, do you think you can have, given an infinite amount of space, like space not being a consideration, do you think you can have too many subs?
If you're competent in placing them
and
configuring them, then no. The caveat being, if you have too many subs, you often then don't have space to put some other important stuff in the room.
That is a great point. And so, you kind of alluded at something there, that just because you add more subs, not excluding infinite, but just say you go from 2 to 3 or from 1 to 2, does not mean for no reason that it's going to get better. You've got to implement it. You've got to place it. You've got to time it. You've got to do all of those things. Otherwise, things could get worse.
Well, I think the word you use that we need to talk about, unless you've already talked about it, in which case tell me to shut up and we won't. But that's this word better. Because when I show my friends some of these layouts for these rooms they're doing, they go, God, you must have so much bass in that room.
Right.
And, that's like someone that owns a big V8 turbocharged 650 horsepower monster. That's like me saying to you, God, you must drive everywhere at 180 miles an hour. Where, patiently, that's just not true. And the reason you have that big 600 horsepower turbocharged, supercharged, nitrous oxide, whatever takes your fancy V8, is so that when you're only doing 80 or 90 miles an hour, there's just no stress. There's just no strain. And in audio, replace that word stress and strain with distortion. One propensity the industry has got is that mythical 105 dB figure, which we attempted to explain in the quite brilliant white paper that some of us have recently written, which is on the CEDIA website. But there's then this, all right, I'm going to calculate so that the maximum sound pressure level available at the reference seating position is 105 dB. Well, that's just like saying, okay, I want to sit on the freeway all day at 80 miles an hour. So I'm going to calculate the amount of power with the amount of air resistance, with the amount of mechanical resistance, to be able to get up and down slopes so that the maximum I can achieve is 80 miles an hour, which is patently ridiculous because, the car would be hideous. And it's a bit like audio systems. When their audio systems are working to the maximum of their capability, they're pretty hideous. So what we're talking about when we say, do you ever have enough subs? It's the more, and here's, I think, a phrase that we're going to end up using a lot today. The more volume displacement you have, it just means that each of those subs isn't working as hard. And the second you ask an amplifier and a loudspeaker to not work as hard, you're putting it into its linear zone. Yeah. And when I say linear zone is you tend to get out of it when you put what you put in. And the definition of distortion is something you get out that you haven't put in. And when you're talking about an audio system, that distortion can come from so many different places. And whilst the hi-fi community will obsess over, oh no, it's the fuse in your plug. You spend $1,000 on the fuse and that will reduce your distortion. Well, whatever, I'm not going to talk about that. But the main distortion comes from speakers and potentially amplifiers being overdriven, and then that interface between the speaker and the room, and then the room itself.
Now, you're using speakers as kind of a broad, that includes woofers. I mean,
yeah,
any speaker. Broad. Okay.
Any speaker. There's no such thing as a distortion-free speaker. Doesn't exist. Can't exist. The second, the thing most people learn at school, energy can neither be created nor destroyed, only converted from one form to another. The second you convert energy from one form to another, there will always be even a tiny amount of distortion. Right. You go from an analog voltage into a series of ones and zeros digital, bit of distortion. You then go back into analog, bit of distortion. You then take electricity and with some magnets and some coils or however the speaker works, you convert that into kinetic energy, the movement of something, distortion. That movement of a drive unit then couples with air, distortion. That air moves around a room and bounces off surfaces and gets absorbed and whatever, distortion. So, I've said this before on some of your podcasts, Ryan. My job as a cinema designer is twofold. Number one, the removal of distractions. Number two, as much as possible, the removal of distortion. Yep. So how much subwoofers is enough? Well, the answer to that. It depends.
Yeah.
And you know, this project of mine, I went down the rabbit hole about a year ago on it, was in so much of what we do and in so much of what we've written about in the RP22 recommended practice, there is a formula, and that formula will get you within a dB or two. As long as you have some decent specs on things, that formula will get you pretty close. Estimating the sound pressure level you're going to get at 1 kilohertz, you know, you can get pretty damn close to predicting what that's going to be. When it comes to bass, however, no one does it. You ask a speaker manufacturer, how many subwoofers do I need? And the answer is, oh, you know, as many as I can sell you, because I want to make some profits. There's very little engineering in that calculation, and a lot of it, people just go, oh well, I built this room and it sounded okay and it was about this volume and it had this many subs in it, and well, if that's what you want to do, fine, but that's not engineering. And the other really tricky thing with bass, especially when you get into the really high end rooms, is the audibility of distortion. Now, is 25% distortion at 10 hertz audible? Not really, but is the harmonic.
And that's the part that a lot of people forget about. They focus on the fundamental, but they forget about the harmonic.
Yep. And that's, tell you a story. I might have said this on another podcast, but different audience. About 6 weeks ago.
Before we go into that, Peter, can you explain what a harmonic is for those that don't know?
Yeah, if let's say you have a fundamental at 10 hertz, you're then going to have a number of different harmonics, which are described as an order harmonic at multiples, direct multiples of that frequency. So you're going to have one at 20 hertz, you're going to have one at 30 hertz, and generally the even harmonics, especially the second order harmonic, actually sounds a bit lush. It sounds warm. So when someone says, oh, this system sounds really warm, there could be a number of reasons for that. This isn't always the reason, of course, but one of the reasons could be, oh yeah, there's lots of second harmonic distortion, just like valves tend to produce. So you might not hear that fundamental, but once you get into the higher order harmonics,
and the fundamental is the tone being played.
Exactly. And you can all see this. Every single person listening here can see this. If you have a simple measuring mic, mini DSP mic 1, and Room EQ Wizard that's free, play, I don't know, 20 hertz through your sub and turn the volume up. And what you'll find is that at relatively low volumes, if you just play a 20 hertz tone, you'll see a big spike at 20 hertz. And the rest of the frequency spectrum will just be the noise floor in your room and your microphone that you're measuring. As you turn the volume up, and up, you'll begin to see spikes appearing at the multiples of those 20 hertz. And those are the harmonics. So although you might not hear that distortion that's happening at 20 hertz, you'll damn well hear that hideous third harmonic. And that's going to sound really bad. But what it can also sometimes bring, and this is an irony, it's distortion. It's a nasty sounding harmonic, but it can almost add punch. So, because, you know, those harmonics are occurring at the frequencies that we associate the impact of a kick drum. So it's kind of fake punch, but it's also potentially really nasty. So here's the story. I, about 6 weeks ago, went into the primary school, which in the UK is ages 5 to 11, that my kids, who are now, God, old enough, I've got to think about it, 24 and 25, used to go to, because they had a STEM week. So my wife's a teacher there. I went in there and I did this whole thing about sound. And one of the demonstrations I was doing was I was blowing out a candle with an 8-inch subwoofer. And the candle I had at the distance I had, actually, I don't understand the physics, we blew it out at 53 hertz. But as I was turning the subwoofer up, and I was showing them the measurements, one of the kids actually said, "Oh, that's really interesting. As you go louder, I'm hearing other things. I'm not just hearing what I think I'm meant to hear. I'm hearing other things." And it was, yeah, you're hearing harmonic distortion from a subwoofer getting closer and closer and closer to its, and exceeding what it's really built to do. And this is, this is the question. How many subs do you need? Well, it depends. How big is your space? How low do you want to be able to push it? At what sound pressure level do you want to reproduce how low you're pushing it? Are you using active acoustics, something like Trinov waveforming or Dirac art? They're going to both affect it. Where are your subwoofers located? How big is your room is going to define your room gain. And room gain begins at or around the 100 room mode. And if you don't know what that means, can I recommend seriously that you do the online HAA, Home Acoustics Alliance Level 1 training. It's available on the CD website. It's brilliant. It's self-paced. And at the end of it, you'll have a really, really good grounding in a lot of audio fundamentals. But basically, that's the frequency at which the room stops being a propagator of waves. Waves no longer propagate in that room. And those waves switch over to just becoming pressure. So the room becomes a pressure vessel. And when the room is a pressure vessel, you effectively get gain. It's the 0 hertz mode. The room is effectively amplifying that sound pressure level.
But before we move on from distortion, Peter, we have a question coming from John. I think, right, I'll put it on the screen, but I'll read it out in case you can't see it. So, using multiple subwoofers primarily creates smoother, more consistent bass across all seating positions by reducing room modes. What if you only care about MLP? Now, I would say this is a key point of distortion where even if you're not worried about smoothing out that response, because you are only worried about one seat, you're going to need a really big subwoofer, really, really big, way up north of the 32, like in a moderate sized room, to get enough perfectly linear excursion to get all of your output from one sub without it distorting.
Well,
Would you agree with that?
That's assuming that your seating is optimally placed too.
Sure. But I would still say, and this is where I'm interested, Peter agrees, that a challenge of a single subwoofer is going to be that to get the output you need, you're going to push it probably into distortion.
You very, very likely are. I kind of get the idea of near field subs, but again, only, I don't know if you addressed that last time, but only for one seat. A near field sub, you're coupling so tightly to that seat, but the rest of the room, all bets are off.
Yeah.
So if you're only going to have one subwoofer, yeah, I mean, arguably you could just make it near field, but by fixing one problem, you're introducing so many more. As with anything with audio, generally, if you make one thing better, you're possibly making something else worse.
Yeah.
And again, you've probably already covered this, but frequency response is one part, and I would say the minor part of calibrating a system,
yes,
as opposed to time domain response. Yeah. So if you have 5 subwoofers in a room and you play steady state sound through it, there's no transients, there's no impact, and those subs are driving the nulls, and you're doing all the right things in terms of positioning subs to get a smooth frequency response in the room. What you could end up with is when you play transients, so let's say a kick drum, oof, 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 all of those pressure waves from all of those subs really want to be arriving at your head position at the same time. Now, for multiple seats, that's patently not possible with a big caveat. But yeah, you're by getting a really, really good smooth magnitude response. So when I say magnitude response, frequency magnitude, frequency response, by getting a good frequency response, you're possibly going to end up with a much worse time domain response. And if it's a terrible frequency response, that means you get a really good frequency magnitude response, you probably have to find a balance. And one of the clever things about Trinov's waveforming is that the way that works is all the subs at the front produce as close as possible to a planar wave that moves through the room, which means that in theory, and it works pretty well in practice, everyone is getting really, really good time domain response from all of those subs combined, because that wave's moving through the room. And then if you've done your job right around the crossover, so as the main speakers hand over their bass to the subs, if you've got that aligned, then any bass that's being bass managed to the subs from that front sound stage, you'll also get that nice, coherent, punchy wave traveling through you, rather than, oh, that wave, and then that wave, and then that wave, and then that wave. Now, obviously, it doesn't happen that slowly, but that transient should be all that pressure all at once, not that pressure spread out bits and pieces over time. From the
real thing that I think you lose there, and we talked about this a few weeks ago, is if you're trying to get that visceral chest slam, that relies on very, very coherent arrival of pressure. You know, we're trying to get this instantaneous hit of, you know, no pressure to pressure as a universal bang. And if everything comes from a different direction and at slightly different times, you just don't get, like, you really lose that slam, that feeling that we've all heard at an outdoor festival and, you know, a big outdoor gig where it just moves through you. That is really hard in a small room. It absolutely exists, but it's not a level thing, right? And this was a really key thing, is just turning it up loud. And everybody, you know, it's the amount of times I see this in forums and stuff. Oh, I'm after more kick. I want to feel it in my liver. I want more chest slam. Oh, add 3 dB at 80 hertz.
Yeah.
Add 2 dB at 60 hertz. No. Stop being stupid. Fix your time domain.
Yes. People chase feeling by manipulating frequency and level instead of fixing time. I see this all the time. And then what ends up happening is your bass in that room gets hugely bloated, and you lose the realism, the fidelity, the quickness. It all goes away, and you end up with this kind of bloated mess, which, if that's what you've got and you're happy with it, fine. Doesn't necessarily mean it's right. But I see that time and time again. People will try and fix time by increasing output. Yeah. And
a lot of that frequency magnitude, as Peter discussed, you know, we see it time and time again, that there could be 4 subwoofers in a room, and each one has a completely different set of parametric equalizers on it. They could have 4, 6, 8 on each sub, different from the other ones. Now, they've got this perfectly flat response, but they've changed the phase response of each sub. Yes. So now the time domain is different from, even if you get them time aligned, it's not time aligned across the whole frequency.
Real quick, can you explain why maybe getting a flat frequency response screws up time? Like when you're applying these filters, what is happening? We could have a whole topic on this, but in a pretty...
So, as you're changing, you know, the time and frequency are completely interrelated. So in order to change the frequency response, the filters you use will change the time domain to achieve that. Like there is a free lunch. It does exist. You can use an all-pass filter. There are ways of changing the frequency response without changing the time domain, but it's not like when people typically use an EQ, that's not what they're using. So for every EQ filter you add, it's changing the time domain. Small amounts, but a big shelf filter here, you know, a big notch, a wide bit, a narrow bit, they're all changing phase. That now suddenly that coherent wave, that, I mean, it feels wonderful. Once you experience it, you're not going to go back.
Yeah. And Mike is a simple way of putting this when we talk about that you're changing phase, and I'm speaking from the audience's point of view. when you're changing using like a typical filter, like a notch filter or something, we're effectively changing the position of the driver in relation to positions of the driver from other speakers, right? So the waveform is, when it's being produced, is arriving at your ears at different times, correct?
Yeah, I mean, crikey, we could have a week's
We
worth of
could. I'm just trying to be simple so that people understand when we're in a simple context, when you're changing frequency using a filter, how is phase changing? What is the primary cause of that?
Let's go back to real basics.
Sure.
And I'm going to make the statement that in nature there are no time domain errors. In nature, time domain is perfect, because the thing making the sound is a thing making the sound.
Yes.
It's not that sound being broken up into different frequency ranges and then something trying to reconstruct those disparate sources of sound into a wave. And the other thing to, I think, always take sound back to basics is your ear is a pressure sensor. The only thing the ear can detect is pressure, and the faster that pressure changes, well, that's frequency. So everything we do comes back to two ears, and most of us have hearing in both. What are the pressure differences that appear at that ear, and what are the pressure differences that appear at that ear? And then our brain makes sense of that as sound. So in nature, as I'm speaking, my vocal cords are vibrating. It's going through this resonance chamber that's my throat and my mouth. My tongue is manipulating things. The shape of my mouth is changing. My vocal cords are vibrating at different frequencies, but fundamentally, coming out of my mouth, there is a coherent sound. The second we try and reproduce that sound, we've got some problems, because you can't just have a single drive unit that's small reproduce the whole frequency spectrum. It just won't be able to cope. If it's too big, it'll be too heavy to start and stop quick enough for those high frequencies. And the size of the drive unit will be very, very close to the size of the frequency it's reproducing, which means it will end up being very, very beamy and very, very directional. So what we end up doing is splitting those sounds into different frequency bands. And if you say, let's say have a three-way speaker as your front soundstage, so tweeter, mid-range, woofer, and that's being passed on to a bunch of subwoofers to bass manage it, you've got three different sources of sound on the speaker. Let's say you're using 4 subwoofers. You've got 4 different subwoofers, and all of those arrival times, if it's going to sound natural like it does in nature, all those arrival times have to be perfect. There can't be between drive units phase mismatches. Again, in nature, there are no phase shifts. In nature, there is no group delay. If I hit a drum, it's, if you go to a live gig and there's a drum kit in front of you and someone is hitting that bass drum, you can, and then the tom, you can feel that. That's visceral, that's impact, because there are no time domain errors. The second we start processing it, we're sampling it at 44.1 kilohertz or 48 or 192 or whatever. That's being put through digital filters. That's being brick walled to get rid of digital noise. It's going through an amplifier, and no amplifiers are completely linear, yada, 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 yada. All of these steps in audio. And then the worst one, it's being split into all these different things. That doesn't happen in nature, but that's kind of like the Holy Grail. The Holy Grail is a totally coherent, zero group delay, absolutely the same arrival time at your ears from every single frequency. And that's really, really hard.
Yeah.
And even with loudspeaker designs, there's going to be the companies that say, oh, but coaxials fix this. And yeah, they fix that. You've got one coherent source. So as you move your head up and down, you're not going to change the relationship between different drive units. But they also introduce another set of problems. You know, we'd really go down the rabbit hole if we started talking about all the different speaker types. But the point being is there's no perfect solution. You know, you can't say that this is the best speaker, this, you know, always use sealed or always use ported or this, that, and the other. What we always have to look at, though, is, you know, what are the measurements of that speaker? And the critical thing is, and this is where voice is perfect. My voice has perfect sound power. My voice has perfect off-axis response. If I'm talking and you move that microphone around me in anechoic, you're not going to get all that weirdness that happens with a loudspeaker. It's going to be beautifully smooth. That, you know, that directivity index slope is just going to be a flat line. And you know, that's affected by the shape of my head and, you know, the shape of my nose and my hair to a certain extent. But in nature, there are no time domain errors. So everything we do to reproduce audio, you have to have in your mind. And, you know, to me, frequency domain, it's much easier to correct. We're quite tolerant of it. One of my best friends, James Chen, who owns Chords, the cable company, he's a classically trained musician. And within a couple of bars, he will tell me if it's a Steinway, a Bechstein, a Yamaha, or a Bosendorfer, if it's a Steinway, what model Steinway it is. And he'll have a good punt at who the pianist is. And every time I then look at the sleeve notes, I go, for fuck's sake, well, can I say that? For crying out loud, James, you know, that
you just did, so it's okay.
you know, that's outrageous. But because he's so frequency domain tuned in a way that most of us aren't. But the thing we're all pretty frequency domain tuned into are voices. We just know when vocals are inherently wrong, when they're a bit through sort of plummy or a bit sibilant, or there's just something wrong with vocals. We inherently know. And that's why back in the days, all of the BBC engineers, you know, when they were designing those famous BBC speakers, they mainly used voice to tune their speakers, because it's just instantly obvious if it's wrong, because there are no time domain errors in nature. There's no time domain errors in our voice. So I would always prioritize really, really good time domain response in my design. And then you can figure out the frequency domain response. The problem with the industry is everyone's obsessed with the target curve.
Yeah.
Everyone's obsessed. You draw the target curve, you press the auto magic button, the processor tells you it's done its job. If you're a professional, you then say to the customer, oh, I've calibrated your system, give me lots of money. No, you haven't. You might have made it worse. You very likely could have actually made it sound worse, because getting that time domain right, in our experience, is something that none of the auto EQs do. You've got to let the auto EQ do its job, and then you've got to go in and tweak it afterwards.
Now,
that's only if you've designed your room right.
You kind of gave a broad topic, but this is something that comes up all the time with, especially with enthusiasts, is you mention it with a target curve. I want a flat target curve. And they hammer these target curves, especially the low frequency parts of these target curves, with filters. Why is that potentially a bad idea? Specifically with subs. Let's throw speakers out for a minute, or for this podcast. Why is that a bad idea with subs, and what can that create? And if you're going to calibrate, and then we'll go back to the topic of this particular episode, if you're going to apply potentially a filter, is it better to do a high Q or a low Q?
Generally, the higher the Q, the more the phase response is screwed up. So lower Q, in other words, a low Q is a very broad, shallow kind of filter. A high Q is a really, really spiky notch.
And when we're talking about Qs, for any of the enthusiasts that are watching, if you're in like a mini DSP or something, your Q is typically a number, and the higher that number is, the higher we're talking about the Q being, and the more narrow that filter is going to be. So the less of the frequency range or the less octaves it's going to cover. A lower Q, so like a 1 or a point something, will be much broader and it will cover more of the frequency range in a broad sense.
So the difficult to talk about without bringing one up and showing one. There are potentially, let's go back a step.
Sure.
Let's talk about blending in, blend, kind of a good phrase, blending in your speakers with your subs.
Okay.
So you have your speakers working. As they get lower and lower and lower, they're handing off the bass to the subs at a crossover frequency. But that crossover frequency is not a brick wall.
Yes.
It's not everything above that goes to speakers, everything below that goes to sub. There is a filter involved. And generally, most of the time, that's a 24 dB per octave filter. So from 80 hertz, as you go 1 octave above 80 hertz, and 1 octave above 80 hertz is 160 hertz. By the time you get to 160 hertz, that's 24 dB down at one end.
Mm-hmm.
From 80 to 40 dB, that's 40 hertz rather, that's 24 dB down at the other end. That filter introduces phase shifts.
Mm-hmm.
You can see it. And there's 3 different ways of figuring out your timing of your subs versus your main speakers. The first one is with a simple impulse response. So you play an impulse through your speakers, you then play an impulse through your subs, and you adjust the time alignment to get that impulse in line. That's first one. Second one is to look at how at that crossover frequency, how you get frequency cancellations and you get frequency reinforcements. So at certain time alignments, you're going to get a much smoother frequency response. Mm-hmm. The third one, which is my preferred one, is in Room EQ Wizard under spectrograph, there's a feature called a wavelet. And a wavelet plots energy over time. But actually what it's really plotting is pressure over time. High energy is high pressure, and it's measuring the sound from the lowest frequency you tell it to the highest frequency. And in an ideal world, you want to see that pressure over time being a flat line.
Yep.
So every frequency is arriving at the same time. In practice, or I'd say impossible to achieve. You're always going to have that curve sloping up at low frequencies because of the group delay of a sub. So the first thing you want to look at is at around the crossover frequency, is there a step? Can you see a step? So you might have the speakers sort of coming in like this, then there might be a step and then the subs. And what that means is the subs are delayed. The pressure arriving at the microphone position from the subwoofers is delayed relative to the sub. So around that crossover frequency, remember we said, you've got either side of it, it's shared. There's some energy coming from the speaker and some energy coming from the sub. If that's misaligned by 10 milliseconds, which is entirely possible, entirely possible, rather than that kick happening, boom, you've got a kick from the speakers, and then 10 milliseconds later, you've got this amorphous kind of kick coming from the subs. That's not going to give you that punch.
So there's an important reason why the wavelet works here for this, right? So if you were just aligning this looking for summation, if we were just looking at frequency magnitude and we were using that as the only thing we looked at to adjust the timing to get this alignment, you could be a full cycle, 2 cycles out. So using the wavelet.
When you say a cycle, what do you mean?
So obviously the cone is moving in and out, right? Mm-hmm. At the crossover, probably 80 times a second. Well, you could be a full cycle of that going in and out of alignment from one to the other. So even though your summation looks correct,
can I share my screen?
Unless, as Peter said, you're looking at
I don't know.
I mean, if
do you
digs
have
into
a
his WhatsApp, have a wavelet I sent him about a month ago that we showed on screen.
I think I can. Can I try?
You can try, absolutely. I may have to give you permission. There it goes.
Can you see my screen?
There you go.
Yep.
There you
Look
go.
at that. Look at Peter.
Look, this is well, I'm not measuring this live, but I'm showing it to you live.
Hey,
this
you don't have to tell him that. This could all be live, Peter.
This is a wavelet. And as you can see, ignore all this stuff. That's actually a rattle in this particular room. It was more a lab than a demo room. But you can see that dotted line is plotted. There's a little bit of a step at 300 hertz. I've no idea what's causing that. But can you see through the crossover area? That's really, really
Nice
smooth.
and smooth.
Oops.
Oh dear.
So what do you think bass impact is going to sound like that versus that?
Muddy.
You're gonna hear a really, really, really obvious difference between that and that. And by playing with different filters, I mean, yikes. By playing with different filters, different crossovers, this is just us mucking around. This is just us in play mode. This is a really, really good room. None of these are the final results. This is us deliberately breaking it and just trying different stuff, different filters.
If Peter goes back up a couple, you'll see what's right. So one of the things we were experimenting with here was using all pass filters and a whole load of other crazy techniques. This was genuinely an experiment. We didn't know what we were going to find or what it would sound like.
You mentioned all pass filters, and I'm playing advocate for the listeners. What is an all pass filter in a broad sense?
Essentially, it allows us to change the time domain without the amplitude. This is what we're doing. We were causing a phase shift on purpose without changing the amplitude. So what you heard in terms of level did not change, but we were changing the timing it arrived. And some of these, that arrival line was flat all the way down, like a straight line, ruler straight, to about 20 hertz. I think up 2 or 3 more, you will find them. Really, really flat in the whole range that you can hear. Below 20 hertz, you can't hear it, right? There is a difference in impact around that, but you're not hearing that anyway. But once you get this line, that's now flat down to 40 before it starts creeping up. This is not the natural behavior of that speaker and sub. That sub's natural behavior is to have more group delay. By the time you get down to 10 hertz, it has more delay than this. So we've used this graph and a host of other measurements to try and essentially this was an experiment to see how it feels when you get that line as flat as possible. So it's fun. Research has been done that shows that 20 milliseconds of group delay can be audible, but it was done in a really, it's done in the only way you can do in a lab. So it's headphones, it's intentionally introducing it. They're taking the signal and they're introducing the group delay into the signal on purpose to say, right, can you hear the difference between it with it in or out if we do an ABX test? This is not what we were doing. This was not scientific. It was right, well, let's change the shape of this. That one, almost no group delay down to 25 hertz. How does it feel?
Now I'm going to throw another one at you. We talked about all pass filters. What is group delay?
So you'll see that from 80 hertz, that is naturally rising in delay. So there is a delay that is inherent, like that subwoofer with the design of the product, that's inherent. Any filters we're using, so if we're putting a boost in to raise the level, that subwoofer does not output as much at 10 hertz as we really would like naturally. Yes. So we might have a 10 dB boost at 10 hertz. We might even have more than that. We've got jobs where we've gone beyond 10 dB boost at that.
And to clarify that for people, we're talking about the natural roll off of the sub.
Correct.
So if you're coming down, On a sealed sub, you're probably going to start having significant roll off without DSP at like, correct me if I'm wrong, like 30 hertz, and it's going to start rolling off at 12 dB per octave.
Right.
That doesn't mean that you then can't apply a boost down low up to the maximum power handling and excursion for that particular driver. So you can get that back, and you would boost targeted those frequencies so that it would more align flatly with the higher end of the response of that particular sub. But when you do that, as we've mentioned throughout the course of this podcast, you are changing things. So there is no free lunch with this. And I think this is actually, and you guys can sum things up, but this is actually a really good transition point, I think, to the benefits of adding more subs, that you can benefit from things more if they're properly implemented in the analog, more than you're going to be changing things potentially in with filters and all of DSP and that kind of thing. Cool.
Yeah, I mean, the number one rule of when you're looking at subwoofers is do as much as you can in physics before you then start relying
I'd say in general with sound, as much as you can in physics.
Yeah.
Before you start dealing, what I tell dealers with MadVR, because I do all the technical support for MadVR, is I say, you cannot fix at a fundamental level physics with software, right? It's not going to happen. There is always something that you're going to give up or make worse. You may be able to fix something very minute and specific, but you're going to create other problems if you can even address it at all. And that's perfect for here. The more you can fix in the analog, Peter, as you said, with nature has perfect time. The more you can fix an analog, the closer I think you can get to that natural feeling of instead of mucking with adding DSP and filters and all of that stuff on top of it.
So there's a key thing here of what you can't fix. And this is where I'm going to now get Peter to start getting technical. So
good.
We just said that we can boost up like some of that roll off to the limit of what that subwoofer can do, you know, be it its power handling or
you can.
The reality is that speaker hits a limit called its volume displacement. And we mentioned this at the start. Now, there was a question, I'm not going to dig back to exactly which one it was, but it was kind of like, are we talking about 10 subs or 4? You know, a lot of the questions we've got that we will dig back into. The reality is you're going to need enough volume displacement for the SPL level that you're trying to achieve in the room that you've got. And there's another one about, you know, what happens if I put 4 Ascendo, let's say they're 18s, he's put 16 to 19s in the corner of each room. What will I get? What can I expect to get from those? So with a physical limitation, Peter, let's talk about how we can go from what that sub can physically do, its maximum excursion, to how loud that might play. Run through some chat of how we're going to get to that number.
So we need to have a working assumption for the first part of this conversation, and then we'll try and explain the other half. So for the first part of this conversation, the assumption is we're using sealed subs. Okay, we'll approach ported subs in a sec, because all of us, if you think this next bit's complicated, ported subs are going to get really complicated. Yes. So we're using a sealed subwoofer. And if any of you are physics majors, I'm a mechanical and production engineering major, so I did none of this at university. You would have done something using the pressure equation. And the pressure equation is, you know, a very, very standard thing in physics. Now, a derivative of the pressure equation is if you know how much surface area you have, and you know how much air that surface area is displacing. So in other words, the surface area is how big is the radiating area of your sub. So, you know, not necessarily the basket size, but the actual part of the sub that is pushing air. You know how big that is. and you know what the linear X max is, and the linear X max of a sub is from its resting position, how far can it move in either direction whilst staying linear? Now, this is the bit that always gets giggles, but I have to do it. This is a subwoofer. Yeah, you
know where this is going.
He's going there.
This is a subwoofer voice coil, and this is a magnet. So you have your voice coil moving over a magnet, and as it moves over that magnet, if it moves too far, bits of that voice coil are going to go outside of the area that it's getting that magnetic engine effect. So the further it moves, the less and less and less and less efficient it gets. And there's a point where if you push that sub too far, it becomes non-linear. So linear X max isn't how far you can push it before you break it. It could go a lot further before you break it. It's how far can you push it before it starts going non-linear and your distortion starts going through the roof. And that's your X max. And your volume displacement is effectively twice your X max. So from its furthest position back, how much air can it push out on one cycle? So out and back, out and back. That is the volume displacement. And from that pressure equation, there's a derivative, which is the sound pressure level that you can produce, that the loudspeaker can produce, is 20 times log₁ of the frequency you want to reproduce squared times the volume displacement in square meters. So 1 litre volume displacement will be 0.001 square meters, plus a constant that's another derivative. And anechoically, that constant is 102.5.
What's the name of that equation, Peter, so that I can post it?
Oh, I don't know that equation. I can send it to you. I'll
send it to me.
We'll put it in the chat after the live ends. We'll put it in the chat.
I'll find the equation written down and I'll email it to you. But it basically says that, and the frequency squared thing here is the key. As frequency halves, it's the inverse square law. You've then got to move 4 times the amount of air to maintain the same sound pressure level. And moving 4 times the amount of air also requires 4 times the amount of amplifier power. So you're in kind of one hell of a cycle here. So when someone says, is this enough sub? Well, the question I have to ask is, number one, how low do you want it to go? And number two, how loud do you want it to go at that lowest frequency? Because that sub is going to be working hardest. It's going to run out of displacement at the lowest frequency you're trying to reproduce.
Well, and this goes back to what you constantly hammer on people is you've got to define the room and the expectation of the room before you can figure out what you need in order to meet that expectation. If you don't do that, you're just, how do you get it? You're throwing darts at a dartboard in the dark, but that dartboard isn't even there.
It completely, everything is down to level of expectation.
Yes.
And there was one post where someone says, I think my theatre's okay, but maybe I should come to London, which is going to be really, really bad for my checkbook, because then I'll experience a theatre that I'm going to go, oh heck, I need to.
Foundry is bad for checkbooks.
I need to spend some money. But the realities of bass is it gets very, very space intensive and very, very money intensive really, really quickly when you start wanting infra, because then you just need lots of displacement. And that's why companies like Ascendo make these huge subwoofers that people look at and go, well, that's just ridiculous. Well, no, actually, it's not ridiculous. It's the amount of air you need to move in order to generate those single-digit SPL numbers at the kind of sound pressure that we can feel. You're not going to hear it. Oh, but boy, can you feel it? It's real.
Is it 4 times the power for every octave you go down when you start getting down that low?
You need 4 times. You need to move 4 times the amount of air every time you halve the frequency.
Yeah.
And the amount of power you need, well, it's within its linear X max. The more voltage you apply, the further the drive unit is going to move. So that manufacturer should tell you what voltage is required to push that speaker to its X max, and then
should.
Yeah, but
yeah. I mean,
the things they should tell. So one of the things that is really interesting, like especially on an active sub. So if you do your calibration at 80 dB, oh look, it plays down to 15 hertz, because at 80 dB, you know, that 15 hertz with the subs you've got, you're not pushing the excursion to its very limit, so it's fine. But what most active subs will do is, as you raise the level, they're going to apply almost a dynamic high pass filter. So it's going to say, right, well, you've now already reached, we're now at 30 hertz, but you've already reached the excursion limit. We can't just keep going lower. There's no more movement to go. So you find that as you raise that level, if you do a sweep at 80, 85, 90, 95, 100, you'll know exactly when you found your excursion limit, because 15 hertz will just stop getting louder.
Well, to a certain point, the best way to look at it is, and you will pass this eventually, is as you get to that, the closer you're going to get back to that driver's natural response. As it starts rolling off, you can't boost it anymore. So you're going to come back into the natural.
You've reached its
response
at limit of physics, right? And this is that point of, you can't beat the physics. Once you are moving that cone as far as it can go, there's no more pressure you can get. So if you're already moving it and you turn the gain up, a good subwoofer, generally, I might be being unfair here, but a good subwoofer will protect itself.
Yes.
By not allowing you to overdrive it. Like if it's an active system, there's no good reason really for them not to have some protection in there.
I should say good active subwoofers.
Sure.
Because if you have a passive subwoofer, odds are it's probably not going
different story from a passive sub.
Yeah.
One thing to be clear, we're talking different things when we talk about the natural response of a sub and its volume displacement capability.
Yes.
Those are different things. You can have huge subs that, if you look at their natural frequency response, they start rolling off at 50 hertz. That's the natural response of that speaker. But what you have to do is then boost those lower frequencies, which you can do because they've got lots of volume displacement to allow you to do that boost.
I'm going to find one real quick.
Yeah, you can keep boosting it until you run out of displacement, right? And
or maybe this should be another podcast that I'll definitely leave in your capable hands, Ben, because you're way better at this maths than I am. You run out of gain structure to do it.
Yes, we haven't done an episode on gain structure yet, and I'm not prepared to do that in the next 5 minutes before we start doing questions.
No, which is why I said,
let's push
that to a separate podcast.
Absolutely. Gain structure is a separate hour.
You can run out of gain structure at certain points in your system before you've run out of volume displacement potentially.
So here's one.
There you go.
So this is a huge sub, but you can see that its natural response, 12 dB per octave, just before 30 hertz, you start rolling off. So that doesn't mean that it can't play super low, but in order to get that and get it linear, you're going to need to boost. But when you pass the limits down low, you're going to clip. And that's what I mean by it returning to its natural response, because you're going to hit the limit and the sub is going to start to want to return or be limited to its natural response. And then eventually it will even start clipping there as you start pushing further and further past that.
Yeah, it's interesting what this shows that many don't. And this is a really useful thing to see, because we've got that red line, the maximum voltage passed. So if you're playing this at low level, you know you can boost those bits, but you can't boost 10 hertz on this sub beyond 110 dB.
Nope.
So
theoretically you could if you had more voltage. We don't know. Maybe they ran out of voltage.
Sure, we don't know if a test ran out of voltage or it.
They're already sending it 450
volts.
Yeah,
I don't know any or many amplifiers that can supply 450 volts.
That is true.
That is quite some amplifier they're using.
That is a lot.
Stop condition may have been hidden because of distortion. In theory, you then could go louder, but you'd have to sacrifice.
Yes.
This test.
I'm playing devil's advocate if we don't have that data, so I don't know.
Right. So this is a really key thing, though, that you can now see. Well, that's great. At 20 hertz, I know what we can do. I know what we like, how much lower we're going to be at 10. So we could basically flatten that out. If you chose to, I could go into EQ and I could flatten that out so that it sits at 110 dB from 10 hertz to 100. Great. Now I've got no roll off at all. Like I've managed to EQ this thing flat to 10 hertz. But that means now if I need 115 in the room, well, I'm going to need another one.
Yep.
Maybe more than one. Like this theoretical 6 dB that we'll get, you don't always get. Like it's quite complicated when we do this pressure equation that we are relying, like, so we sum the volume displacement, right? The volume displacement, it's you've got 10 subs, they're all identical. That's a good fundamental place to start. We take our cone diameter, we take our excursion limit, we get placement in liters. We are absolutely relying on them being coherent. If one of them is out of phase or has a timing error to the others, that summation does not exist. So it's easy to say, right, I could make this sub flat to 110. I'll add another one with another amp. I'll get to 116 in a perfect world. Likelihood is in that real room, it won't be perfect. I will not get all 6 dB. Do you agree, Peter? Am I being unfair there?
You're not being unfair. I mean, I'm looking at this frequency response and thinking, well, number one, I'd need to know what your room is. And how big your room is, because room gain is going to have a massively important part to play. And secondly, you know, where are you doing that EQ? Are you doing it in the amplifier? Are you doing it in the processor? Are you doing it in a separate EQ box? And again, this is a different conversation. And one question from Stephen: can you remind us, should we be implementing our shelf filters to push the low end before or after our calibrations? I assume before, so optimizer and Dirac can properly time align. Well, if you stick a flat target curve in really low, both optimizer and Dirac are going to try and apply filters up to the maximum you're allowing it to do it to boost. But you know, if you bring back that picture again, Ryan.
Yep.
We're at 140 here, and that's then down to 110. You really want to boost that by 30 dB? You know, where in your signal path are you going to potentially find either a 30 dB cut or a 30 dB boost?
And this we will have to cover, because this is where you really can run out of gain. Yeah, you may not have enough output from your preamp to even apply a 30 dB boost.
So when, you know, one of the great things about adding lots and lots and lots of subs is it makes this EQ far easier, because you're unlikely to run out of gain structure in terms of amplifier gain, because each of those subs is being driven a relatively small percentage of its capability. So because you've then still got headroom in those amplifiers, you can drive them differently. And this, you know, it's going to be if you guys tackle it, this whole gain structure thing, I think you're going to need lots of pictures and lots of numbers and a big fat spreadsheet to show, you know, that entire gain structure through the system. But to answer Stephen's question, as with most of the answers in this industry, it depends.
Yeah.
It just depends where you have the potential to do to do that gain. If you have the potential to do that gain in an external DSP, I would probably do it in an external DSP before I ran Dirac or before I ran Optimizer. So get the thing as flat as you can, as extended as you can, so long as you've got the gain structure, so that Dirac and or Optimizer are seeing that extension
and
are not then trying to apply that boost themselves.
Making sure you're also within the limitations. I know at 110, you're probably outside of that. The limitations of the test tone, so that you're not pushing to the limits and then clipping when Dirac or Optimizer, whoever's trying to apply whatever boost it thinks it's trying to do. And then you also want to make sure that when you're playing back the signal during use cases, you're not exceeding potentially that boost that it used to try and fix things, because then you're going to be clipping on when those filters and other things are being applied.
I'll say it for free. I wouldn't trust Dirac or Optimizer at 10 hertz.
No. Absolutely not.
I wouldn't trust it in a million years.
I meant just in general, not at 10 hertz. Absolutely not.
Oh, absolutely not. Once you've let the Auto Magic thing, and they are brilliant, don't get me wrong, they're freaking brilliant. Once you've let those things do their thing, you've then got to verify it. You then absolutely have to verify it.
Would you trust a mini DSP UMIC 1 at 10 hertz?
No.
So we have a challenge, but verification, I was going to say below 15, but that may be unfair. But verification at very low frequencies.
It doesn't like you.
Yeah,
Oh, there it is.
There's your focus. Even verifying at very low frequencies needs specialist equipment. You know, we've had a discussion. If you want to calibrate your microphone at 10 hertz, calibration tool to do that is many thousands of pounds. There's only one that, you know, there's a Grass calibrator, it's lab grade. You're not calibrating a microphone in the field at 10 hertz. So once we're down to 10 and lower, things are, you know, all bets are off almost. You're kind of going by feel, and just don't push it so far. You're damaging things. Keep the distortion as low. I mean, I say this, but by keeping that distortion down, because you will introduce harmonics. If you really do reproduce that a lot at 10, the harmonics at 20 and 30 are audible. Like, so you've got to stay within the realms of what that product is happy to do. It's not just a matter of pushing it and pushing it and pushing it to, like, the smoke not coming out is not enough of a, okay, it's fine.
Microphones are important. That's my, you know, one of my 2 infra mics. These are $2,000 each.
Which one?
It's a PCB Pizzatronics half-inch capsule XLR goes into an interface. You know, I trust that. It's a lab grade microphone. I had to sign a disclaimer when I bought it, saying I wouldn't re-export it to Iran or China. Basically, it's that kind of, you know, this is an accurate thing. Microphones can and often do lie. So the whole infra thing is, all right, you can kind of see what's going on with the microphone, but at the end of the day, we all kind of adjust that by ear.
Yeah.
You know, we'll look at it on a graph, but then we'll listen to that on a range of content that we know that's got infra, and just go, is this okay? Because at those kind of frequencies, interesting, from Mr. Stekeli 1980. My bank balance chose transducers and imagination from Photonic. It's a very fair comment. Really fair comment, because our perception of infrasonic, it's visceral. We're feeling it. So if you're on a flimsy resonant riser, that's going to be a very different visceral feel to if your chair's just sitting on a concrete floor.
Yeah.
And then what's the chair made of? How's the chair going to resonate? You know, there's so many things that come into it, that just because you see something on a graph, that's not really describing the experience you're getting. The graphs get you in the ballpark. Graphs tell you that nothing is fundamentally broken. And then the cycle is measure, listen, adjust, measure, listen, adjust, measure, listen, adjust. And at every stage, the graph will tell you, okay, I haven't broken it. Now, does this sound good? And then if you have the option of presets on whatever processor you're using, you have the old one against the new one. You listen to that on a range of content. Is that better? Good. Let's try and iterate and iterate and iterate. But one thing, you know, I know we're now talking about calibration, which isn't the topic, and we still haven't really talked about how many.
We're going to go back to it right after this.
Go back to it. One of the things I always do is at the point that I think, yeah, this sounds okay. This is pretty good. Save that as a preset and don't touch it. That's your baseline, because what you can end up with in calibration is a spiral of deceit. You're convincing yourself this is better and better and better, because human nature is, oh, it's different, so it must be better. And every once in a while, just go back to that early one as a kind of a sanity check, just to check, oh, no, okay, actually, I've made it worse. Right, back to square one.
And don't fiddle too long.
And back to square one is usually, I'm going to stop and come back tomorrow because my ears are now toast.
I can't remember the amount of times I've left Foundry at 2 or 3 or 5 in the morning, and I've texted you and gone, oh, I found this amazing thing. I was just experimenting and it turned into an all-nighter and it's amazing. And we listen to it in the morning and go, that's awful. That's terrible.
Yeah. It's exactly that. It happens to everybody.
Yep.
So back to the how many subwoofers you need. You know, there's that HBO series Chernobyl. Yeah. And in the final episode, there's a courtroom scene. And he has a number of bricks, and you know, these are the things that keep a nuclear reactor in check. These are the things that cause a nuclear reactor to run away from itself. And if you remove too many of the things that keep it in check, it's gonna run away with itself. And when you're looking at SPL in a room, it's kind of the same. That these are the things that add SPL. And then these are the things that then take SPL capability away. So the things that give us SPL is, you know, firstly, the volume displacement of the subwoofer.
Yep.
Haven't talked about ported subs. Will if we have a chance. Secondly, does the amplifier have enough voltage to drive that subwoofer to its maximum volume displacement and sustain it? You know, amplifiers doing 3 hertz, that's really tough.
Hard.
It's obscenely tough. Don't think, oh, this is a great amplifier, it's really expensive, it can do 3 hertz. It probably can't.
And your power supply might not be able to. Like physically, we've tripped breakers. Like, so it's not just can my amplifier do it, it's can the wall socket my amplifier is plugged into sustain this.
So volume displacement, and then if you put that subwoofer against a boundary, the reason subwoofers are omnidirectional is basically to do with the fact that that drive unit is tiny compared to the wavelengths it's reproducing.
Yep.
The wavelength of 20 hertz is 17 meters, which is what, 54 feet. That's huge compared to even a 64-inch subwoofer. You know, it's small. So although the subwoofer is, you think, kind of putting all the sound out that way, it isn't. It's emanating pressure in a 360-degree hemispheric way. So if you hang this subwoofer off a crane and you measure it with a microphone, that's what we'd call anechoic. You're measuring that speaker with no boundary effects. The sound is radiating out of the sub, and it's going away. If you put that sub on the ground, you're no longer in free space, you're in half space. So the energy that would have been going, if that's the sub on a floor, the energy that would have been going that way is instantly being reflected that way. Now, if that surface is completely rigid, the theory says you get 6 dB of gain, twice the power. If you put that sub on a floor wall boundary, that's now working into quarter of space. All of that energy is being concentrated into a much smaller space. None of it's going down. None of it's going back, you'd like to think, except much of it does. So you then get 6 plus 6, 12 dB. Excuse me while I sneeze.
So I'll just say why Peter sneezes, that we can prove all this mathematically really easy. So if you just look at the surface area of a sphere and you cut it in half, or you cut it in a quarter, what this propagation is essentially the surface area of a sphere. So every time we cut it, the maths equations absolutely stack up to what we're saying is going to happen, because it does. The sphere is getting smaller. The formula shows absolutely these numbers that are theoretical completely stack up.
So this is what we call boundary gain, that you're slicing that sphere, and that energy, rather than emanating all around that sphere, is being focused into one area. In reality, you rarely get 6 dB, and that is because in reality those surfaces are never completely rigid.
Yes.
I did a lot of work in big palaces in the Middle East, and the basis for those rooms were reinforced concrete. So when I was talking bass in a fundamentally reinforced concrete box, we were getting pretty much close to 6 dB off every surface, because that box is really rigid. In the US, your houses are built of sort of papier-mâché, balsa wood, and a few sticks. And
unless you're in the basement,
if that wolf came along, it very
Won't
well
keep
might,
the 3 pigs happy.
no, it will blow the house down. And we've all heard this. We've been in a cinema and thought, where's the bass? Where's the bass? And then we've gone to the restroom, and
there it is.
The other side of the house. There it is. Found it. Here it is. Everyone over here. Bass. The second bass escapes from a space. It's really, really, really unpredictable. So we can't rely on 6 dBs worth of room gain. And what room gain you're going to get, I mean, it is predictable. You do some boundary element modeling and some sophisticated stuff, you can model it. But even across a wall, it's probably not consistent. Towards the corners where the wall's more rigid, you're going to get more gain than if you put that sub in the middle when the wall's more flappy. So boundary gain is an important thing that gives us more. When you then have multiple subs, again, it's not as easy as you might think. If you have 2 subs and you stack them, again, the theory says, well, twice the amount of power, 6 dB. That's only if those 2 subs are closer than a quarter of a wavelength that they're trying to reproduce. So the wavelength at 80 hertz is what, 343 divided by 80, about 3.8 meters. So a quarter of that, we're talking, 2.5 feet or something. So if those 2 subs are within 2.5 feet of each other, they're going to couple really, really well, and you're going to get close to 6 dB. The second you spread them around a room, so let's say you put one in each corner, well, all bets are off. Are they coupling? Not really. And then you're adding time delays to the sub. You're looking at that magnitude response. You're trying to cancel out some room modes. So those subs are not being phase coherent. So rather than adding 6 dB every time you double the amount of subs, you can probably only realistically add 3. Then you've got room gain, and room gain is effectively the 0 hertz mode. Now I know that sounds 0 hertz. What? Well, here's a thought experiment for you. If you have a manometer, a pressure gauge, and you take Ryan's big 64-inch sub and you tell it, move. Yep, move out. Don't move back, just move out. You're pressurizing the room. You should see that pressure gauge move and then stop. Now, if the sub then went back, you should see that pressure gauge then going negative, positive, negative. But if it moves and your room is completely sealed, that pressure gauge should just stay there. And that room is then a pressure vessel. So around the 100 room mode, and you can work out what that is. You take the longest dimension of the room, double it. What frequency wavelength is that? So that's, what's that in feet? 1,130. Is it speed of sound 30 feet per second?
Yeah,
I think it's 1130. I know it's 343 meters, but feet, I think it's 1130. Divide that by twice your room length, largest room length, and you'll get your 100 mode. So below that frequency, you're going to get room gain. And again, the theory says that your room gain is 12 dB per octave. So from 20 hertz to 10 hertz, by the time you get to 10, it's not instant 12. It's by the time you get to 10, you're going to get 12 dB.
Very convenient that matches a sealed sub, right?
Yeah. But for that to happen, that room must be sealed, and the walls need to be effectively rigid. So neither of those are going to be the case. You're going to have leaks. You're going to have air conditioning. You're going to have HVAC. So that number can be anything between 7 and 11. 7, 11. That's an easy one to remember, isn't it? If you've got a rigid, very sealed room, you might get close to 10 in reality. So what that means is, as Ben said, if you have a sealed subwoofer that below F3, so below the -3 dB point of that sub, it's going to roll off naturally at 12 dB per octave. If you then have room gain at around 10 dB per octave, sub rolling off, room gain, you're going to get quite a nice, gentle, flat line. And that's why often in small rooms, we measure them and go, whoa, subs are going down really low. I didn't expect that. And that's because of room gain. A ported sub has below the port. Here we go. A ported sub below the port tuning frequency has a roll off of 24 dB per octave. Now that port tuning frequency is really, really interesting, because a manufacturer of a ported sub has got to think, okay, what's the application for this sub? And if it's in a club, it's in a venue, the application for that sub is basically 45 hertz punch all day long. Just 45, 50 hertz punch all day long, boom, 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 dance music. So that port's probably going to be tuned at around, I don't know, 38, 40 hertz, something like that. And around that frequency, that sub is fantastically efficient. As you get to the port tuning frequency, that port is effectively acting as a Helmholtz resonator. And the sub is barely, the drive unit is barely moving.
Yep.
But all the output is coming from the port. Well, what's the problem with that, I hear you ask? Well, nothing if all you want is 45 hertz punch all day long. However, that drive unit's hardly moving. You've also got energy coming out of that port. Are they in phase? Kind of. As you get close to that port tuning frequency, you get quite big phase shifts. And a phase shift is group delay. That's basically what group delay is. It's a phase shift in the sub. Above that port tuning frequency, you're relying on the drive unit and the volume displacement. Around that port tuning frequency, you're actually getting about 2 or 3 times more efficiency than you would. So huge output at around that port tuning frequency. Below that port tuning frequency, here's where the problem is. Well, not necessarily a problem, but here's where it's not a problem, it's a compromise. Here's where the compromise is. That output falls off a cliff at 24 dB per octave. And if you try and push it lower, effectively the excursion of that drive unit goes up exponentially and it's completely undamped. It's just, in effect, flapping around in free air. So you can't really push a ported speaker lower than its natural response wants to be. And that natural response is 24 dB per octave roll off. So if you want an efficient sub, at around its port tuning frequency, and you're willing to make a few sacrifices when it comes to group delay, nothing wrong with ported.
Yep.
You know, it's not the case that, oh, sealed subs sound much tighter necessarily. Ported subs can be really, really, really great, really efficient. But in most rooms, the sizes of rooms we do, you just can't really benefit from room gain. To benefit from room gain, sealed subs are going to be much, much better.
Mm-hmm.
So you've got gain from boundaries. The theory says 6. If you're going to do a calculation, use 3.
And you can use some pieces of software, but again, like you've suggested when trying to figure out this through an equation, the software in a lot of cases can't take into account building materials, these variables. It can get you in the ballpark, but you're really not going to get closer to that. So it can help with things like positioning, with maybe how many subs you may need, but it's not going to be a perfect answer.
The key thing about any simulation like that is that the output is only as good as your input. So I've sat with some fantastic world-class engineers. Some of it's like, well, that's not, is it? Oh no, but we've simplified it because, okay, so you're looking at how much that wall's flexing, and you're treating all 4 walls as individual walls. But when they meet in the corners are stiffer. Oh yeah, but we're not modeling in this model. Like, don't worry. Like, okay, when we get to the point where some of the smartest people in the world massively simplifying their simulation models, the idea that simple hobbyist, enthusiast, average integrator is going to simulate these things accurately, it's a pipe dream. Just doesn't exist.
I'm going to make a statement, and that is, I think modeling rooms is not a waste of time, but a lot of people put far, far, far more equity in a room model than they deserve. The models are perfect. You can model a room to 100% perfection as long as the input into the model is accurate.
Mm-hmm.
Now, the input into the model, if you've got drywall, you know, if you've got US construction, sure, you can put all the individual elements into the model, but a bit of drywall, they're not all the same. If you get 1-inch drywall, there's 1-inch drywall and there's 1-inch drywall. If you get a 2x4 timber, well, what's its moisture content? How tight are the plugs? If you've put some sort of fuzzy rock wall stuff in the middle, what's the density of that? How much have you put in? Where's it sitting? There's so many variables. So models can get you close. Models can help with a lot of decisions, but models can never, unless you've got completely rigid. If your baseline is that wall ain't moving, the models are perfect.
Yeah.
And that's the model in Room EQ Wizard. The model in Room EQ Wizard, the assumption is either the walls aren't moving, or you've got an absorption coefficient at every single frequency that's the same across the entire wall. It's just not, you know, you put absorption coefficient front wall, you might put in, all right, I'm going to be conservative, 0.25. Really? You really think it's going to be 0.25 at every single point across that wall at every single frequency? It isn't. It will, you know, it will tell you where you might expect to find a second order axial mode, but the reality will, as built, probably be different.
Yeah.
So, you know, my biggest advice when it comes to room modes, if you can, and I know sometimes it's not possible, give yourself a little bit of flexibility with furniture placement.
Yeah.
Even if it's 9 inches backwards and forwards, that can actually make all the difference in the world, because these things are really, really unpredictable.
So
yeah.
Before we jump into all, because there's several questions that
there's a lot to go through today. Yeah.
What is the Aylett equation?
Oh, the Aylett ratio.
Yes.
Well, the Aylett ratio is making an assumption that I can do 10 hertz at 120 dB but I also have 10 dBs worth of headroom to play with if I want to push that even louder. So if I can do 10 hertz at 130 dB, that's an Aylett ratio of 0. Anything less capable than that, I'm going to end up with a negative number. So the Aylett ratio is saying money, no object, perfect, lots of volume displacement. I'm aiming for an Aylett ratio of 0. You know, that's the gold standard.
And that's hard to do.
That's the Aylett standard. Anything less is going to be a negative number. So I've kind of made it a bit draconian that pretty much every single room you can possibly enter into my spreadsheet will end up with a negative number. And that's just kind of a bit of a cheeky joke. But at the end of the day, you can choose, you know, your ratio as this is what I want to try and achieve, and then play around with all the numbers we've been talking about. And the key to the whole calculation is volume displacement. So a lot of subwoofer manufacturers will use CTA 2010, isn't it, Ben? Yeah, we'll use CTA 2010B for subwoofer output. Look, you know, that can be frigged. There's lots of it depends. It falls off a cliff the second you're talking about infra and really, really low excursions. Is it valuable? It's extremely valuable. But I think even more valuable would be this is the maximum linear volume displacement this subwoofer can deliver. And here's either the internal amplifier, and it will sustain that down to this frequency, or this is the external amplifier, and it will sustain that down to this frequency. If we start off with that volume displacement number, then that formula, 20 log₁₀ frequency squared times volume displacement in squared meters plus the constant, which for spherical radiation is 102.5, that will then allow you to start with the baseline of what will that one sub enable me to do. So that sub then goes on to this adds in terms of the side of blocks. You know, that's your baseline. This is what it can do. You can then add subs, increase. You can then have them in phase. You can then have not necessarily in phase. That's going to affect it. How many boundaries are they up against? What's that boundary made out of? So this spreadsheet I've put together, it allows you to input, you know, this is my guesstimate at all these
Have
things.
you ever entered the data from Ryan's room? Steve just asked if what the ratio is for Ryan's room.
I think we should look at the room that you just did in Asia. We should look at the foundry.
I could do that. I could do that live if you like.
Let's live.
Well, let's see what it does.
I'm not going to share the spreadsheet. I'm not going to share what I'm entering into yet because I'm not quite ready for that. So
I think this might be positive.
Ooh, let's have a So
I did go a bit crazy.
Your main subs are 21s, aren't they?
They're 21s.
How many of them have you got?
8.
8 21s. And do you know their volume displacement? So 2 times X max?
It's a 17.5 millimeter X max on an ascender. It's a 21 sealed, right?
Yes.
There's 17.5 mil. I'm going to check that, but I
so
think
sounds right. And the linear X max is how many millimeters?
This is a 35 millimeter linear.
Yeah.
It's really sad that I know that off the top of my head.
So the estimated volume displacement is 11 liters from that.
I will confirm that because I have that in MATLAB.
70 millimeters total excursion. So 35 each side. I'm not sure it is 35. I think it's close to 20.
35 sounds high.
Their own spec says it's linear end to end is 35.
End to end 35.
Yeah, 17.5 each direction is what their spec sheet says.
17.5. Got it. So that's a volume displacement of 5.5. Right. Let's enter that. 8 subs sealed. 5.5. I need data on the 65 now.
So then there's two 32s.
Oh shit! My calculator doesn't go to 3 types of subs.
Oh,
well,
so do two 64s then, effectively.
All right. So a 64 is what's the volume displacement?
I will tell you now. Hang on, I could work this out. I've got MATLAB open, which has its calculations. But let's go with this.
Quite a lot of X math, isn't it?
They list
scary.
The spec sheet lists maximum linear air volume displacement as 105 litres.
Oh, in that case, I'll just enter 105. Cool.
I do enjoy they also give it in US liquid gallons, as if we care about liquid gallons here, but you know.
You do if you carry milk in the US.
27 US liquid gallons. That's one big gulp, isn't it?
There's a crossover between them.
Between the 21s and the 64?
Yeah.
It's around 25.
25.
So your 21s by 10 hertz aren't really doing much at all, and they're almost nothing. They've rolled right off.
How long is the room?
Do we want to do it full length or where the subs are?
Full. What base can see?
Structure.
So the length.
28.
The length of the structure.
28 feet.
So that's 9 meters.
Mm-hmm.
Width.
Should we do it? Okay, 16 feet.
So that's what?
It's roughly 5 meters.
5.5. 5 meters. Cool. And height?
7'8".
So 2.2 meters.
Something
2.3.
like that.
Base extension target. Let's put 10 in.
It's still going to be negative.
Oh, it's quite close actually. Depends what I put in for boundary gain.
It's 8,000 pounds of plywood with 5 sides of concrete.
Okay, in that case,
quite a lot of boundary gain.
So the room is sealed.
Yes.
And I'm going to put 6 boundary. You know what, mate? You're positive. Your room has an Aylett ratio of 6. So at 10 hertz, the prediction is it will do 124 dB.
I mean, that sounds. When we were messing with just measuring when Peter or when Adam and Matt were out, we were doing 115 cruising at 5 hertz. So, and that 64 is 3 feet from you. So that it's not, yeah. Well, it's a fun experience, but I'd imagine your guys' Asia room's quite terrifying as well for what that thing's able to do.
I'd need to check my calculator because I've just thrown numbers in very quickly. I came out at your 100 mode, an absolute peak of about 147 dB if you really pushed it to its max.
That sounds right.
Is that about where you got, Peter? Do you know what? Did you get a dB figure?
Oh, at the first mode.
Yeah.
So at 20 hertz, effectively. So if I enter the target at 20 hertz, and I make the array gain phase coherent, then I get 133.
Okay.
That sounds right.
I tell you, I need to adjust what I've done because I think I've just
having played in there, that's about the limits that I can.
But look, if any of you are good spreadsheet monkeys, you can put this together. That equation that I'm gonna send to Ryan, that's the fundamental thing, that this is what one sub can do, and then the rest of it is just kind of pretty basic.
Yeah.
If you stick it up against a boundary, this is the gain you're going to get. If you have multiple subs together, depending if they're phase coherent, semi-coherent, or incoherent, then you're going to have the room gain. So it's, you know, it's just you build it up and then you take stuff away.
It's a good. I'm anxious to look at that equation because I think it'll be good for people if we're willing to share it, to have a basis for, hey, where am I? Where can I improve? Where subs are kind of this enigma of, I have no idea where I am in this ocean. Give me some direction.
I'm not going to share that equation. I'm going to share the basic equation.
I think that's fair.
20 log₁ frequency squared times volume displacement plus the constants. Absolutely, because that is what it is. But if anyone here has ever been on one of my courses, one of my catchphrases is software is not a replacement for competence. And the problem is if we give the community a piece of software, they're not going to have to learn the physics. I'm very happy to do as much teaching and podcasts and stuff to give people the knowledge they need to put their own spreadsheets together. And once you've put your own spreadsheet together, that means, oh, I now understand a lot more about how bass works in a room. I can make informed decisions around all these different parameters. One of the comments here in Asia, our houses are made of cement. All 4 sides in my home theatre room is concrete. That's both wonderful and a potential nightmare.
Yes.
It's wonderful in terms of room gain and boundary gain.
Yep.
It's an absolute potential nightmare in terms of where does the energy go?
Because remember, it's great to contain it, to increase volumes, but you got to get it out somehow.
Yeah, you don't want it hanging around. You really don't want it hanging around.
And that's why, as an example, my room, 14 feet lengthwise, is eaten up through acoustics to try and manage that bass. And it's got waveforming and art that are also trying to deal with it. But anyway, we've got about 20 minutes. Let's do some rapid fire questions because we do have a lot of them. So let's try not to get hung up on any of these. But you guys have some great questions. So I'm going to put them on chat in the order they came in. So first in, first out. This isn't really a question, but we can provide some insight into it. Stephen Kelly, 1980, says, my first and only calibration in my home theater with my 4 new subwoofers was showing better graphs with 3 turned on before I time aligned the 4th. The 4th added a large dip. We'll try again soon. So I think what he's effectively saying is something that I mentioned at the beginning is just because you add more does not necessarily mean it's going to get better. It can be detrimental.
Yeah, there will be a question of, is that time alignment accurate? Especially depending on their placement. If one of them is at the back of the room, and time aligning subs is not an easy thing to do. You know, we talk about different methods, but the ideal thing that we would do is actually phase align them, taking a phase measurement of a sub at the seating position in a small room is, I'm going to say, almost impossible. It's a challenging thing to do. So the likelihood is that 4th subwoofer was actually not correctly time aligned.
That would be my guess. Peter, anything to add?
Not enough information, really.
Yeah, there's a lot of variables.
You know, where are the subs placed? Are all subs the same sub? How are they being time aligned? What's the method? Yeah, I would in that instance with 4 subs, I would probably start off with an impulse, and then you look at summation, and then finally you look at the wavelet.
John Lim 7720, using multiple subwoofers primarily creates smoother, more consistent bass across all seating positions by reducing room modes, peaks, and nulls. But what if you care about only the MLP? I think it's still a benefit. You can get away with less.
Yeah, we kind of covered this in terms of distortion. If you would need a very theoretically perfect subwoofer to get as much output as you really need from one driver without hitting its distortion point, you know, the point where it ramps up, it would be a challenge.
To Stephen, he's saying there's one in each corner. If that's the case, I'd say that somewhere there is a time alignment problem. You should, with one in each corner, it's a decent place to start, and you're going to get all of that boundary gain. You should be able to time align those pretty well, and also let them do their job with room modes.
And we're presuming they are either all ported or all sealed. If that fourth one is the opposite to the other three in terms of ported or sealed, well, there's a first place to go and look.
You're introducing time issues without introducing your own time issues, if you know what I mean. Big Street Cinema says, are we talking 1 to 4 subs, or is it 8 to 12 or even 16 subs? And he's talking about, you know, the Aylett ratio on the number of subs needed. And I think this goes back to, what is your expectation? What are you trying to do? What are the size of the subs?
What's the capability of the subwoofers? How big's the room? And what do you want to achieve? You then need to plug that into the equation. With the key thing is, you've got to know what the capability of one sub is. And there are not many manufacturers that you can get that data out of. You know, there's not many manufacturers that you can say to them, tell me what the linear volume displacement of this sub is. And if it's a powered sub, so the amplifier is built into the sub, you can then ask them the question, tell me what the lowest sine wave that can sustain and for how long.
Yeah.
And they will probably not understand the question.
And guys, this is without data, without knowing your inputs. How can you know what the output is going to be? It's not possible. No. You cannot solve the equation without knowing what's going in. And this is what Cedia and Peter and Ben are really trying to hammer from manufacturers. And we won't linger on this, but without data, especially in home theater, how can we have an expected result?
The only thing I'll say is, every single speaker manufacturer on the planet requires data on every single component that goes into that loudspeaker.
Yes.
They, you know, every resistor, every inductor, every capacitor, every circuit board, every cable, every connector, every speaker basket, every cone, every voice coil, every magnet, everything, the fuzzy stuff, the wood, the cabinet, the bracing, they require data on every single element that goes into that speaker so they can predict the result. And my product as a cinema designer is the totality of the room. It's, you know, my product isn't a collection of lots of stuff. That's just the building materials. My product is the totality of the experience. And I require data on every single element that goes into the product that I'm building. So the more you can all go to your manufacturers and go, where's the data? You know, give me the data. Unless we all do that, they're not going to give it to us.
And I would say be supportive of the ones that are providing that information, because they're doing it at the benefit of you and they're not hiding behind anything, regardless of what the capabilities of their speaker are, so that people that are building these spaces, and I'm talking specifically our industry, are able to do them in a very objective way. King Teaspoon, speaking of seating, more rooms prefer a center. This is actually a good question. Center chair for the MLP, but isn't there often a knoll in the middle? So this goes back then to our last week's conversation.
Yeah, I think I covered this last week. It'd be worth going back and looking at the where should they go episode.
Yeah.
So the reality is you can't drive a null from that null. So if you have a subwoofer on the center line, you won't drive that first room mode null. But also, if you have two subwoofers spread equally distant off the center line, and we talked through last week about them being on the quarter points of the room, they will essentially make a phantom sub halfway between them, which will be on that halfway line. It's not going to remove the problem, but it mitigates it.
Yes.
So you can do this with sub placement, with specific absorption. I use tuned absorbers unless it's an OA room, in which case we do acoustics completely differently. But you've got three tools. You've got the subwoofer placement, your tuned absorbers, and your seating placement. Find the best mix between those three. But
and I think you showed this in some of the graphs that we were showing last week. So go back and watch that episode. It is pretty informative with what Ben showed.
And active acoustics now.
Yes, and that changes the game entirely. We focused last week on non-active acoustics because it was interesting to show how room modes work and how sub placement affects it. And as soon as you do waveforming, all bets are off because it fixes most of those problems on its own.
John Lim 7720 with room treatment. My room has an RT60 of around 250 milliseconds. Do you think that is too low, creating a dead room?
I need 2 pieces more information. I need at what frequency is that 250 milliseconds, or is that an average between 125 and 4K? That's the first bit of information. Second bit of information, how big is the room? Because that reflection decay time and what we consider nice is completely dependent on room size.
Usually increases as the room increases in size.
I think we've talked about the formula before that is fairly standard. It comes from it's ITU's BS 1116.3. It's about page 8, page 9. They use a theoretical room of 100 cubic meters. And at 100 cubic meters, they say 0.3 milliseconds, sorry, 300 milliseconds. As the room gets bigger or smaller, that number goes up or down.
Now, I would say this is also can be subjective. This user,
but that's the idealized, the ITU's idealized RT is based on 300 milliseconds in 100 cubic meters. It goes up and down from there. But the key thing, as Peter said, is when we look at this for ourselves, we look over 8 octaves. What is important is which way would this be? Hold on. To the low frequency, a natural rise is generally acceptable.
Regardless of whatever happens, you want it to be smooth.
Smooth is,
and this is almost all universal across AV, many different facets. Whatever happens, if you are going to deviate, ideally you want it to happen smoothly, not abruptly.
Right.
Very true. Yeah, great.
Yeah, if your RT is, up and down, up and down, up and down, or if it just crashes somewhere, that's going to sound oppressive.
You're going to notice.
It doesn't, realistically, it doesn't sound like it's going to be too low, but that's making a lot of assumptions.
Yeah. All right. Rapid fire for the last ones, because I've got about 7 minutes and then I got another meeting I got to jump to. King Teaspoon, after my integrator finished my room build, my usable dimensions are roughly 15 by 15. No room for large infra subs. What can I expect from 4 smaller Ascendo subs? We kind of talked about this on the stream, but room gain, I mean, there's a lot of variables that go in.
Not enough information. How loud do you want it to go? How low do you want it to go? And when you say smaller, what does that mean? Smaller than a 64 is a 32.
He has put 16 to 19, so I worked on an 18.
16 to 19s.
Funny enough, the Ascendo 18s don't hit low like a 32 hits, let's be honest, right? So
no,
you've got,
they're still great subs. It's just that they
don't hit 10 hertz in that same way, because they're not really designed to be, even though they're big, they're not chasing 10 hertz because Ascendo makes specific products to do that. They're not designed to
potentially also introduce other variables and facets that I think Jeffrey is unwilling to compromise on.
So if you've got 4 18s in a room that size, it will be truly excellent at 20 hertz. But don't, again, completely depends on the calibration and where those speakers are placed and what your room's made out of, room gain, boundary gain. But don't expect to get lots and lots of infra because you're not
hertz is excellent.
It's great.
That is in a lot of content. I've looked at a spectrograph in real. There's not, I won't say limited amounts of content that get below that, but the majority of content, would you guys agree, is at or above that?
Oh, yeah, absolutely.
Yeah. Absolutely. So don't think that you're missing out on all of the content that's being played. You're not. You're going to have an excellent experience even getting down to just 20 hertz.
I should know how many musical instruments have a fundamental below 20 hertz. I'm sure I can count it on one hand. Obviously, a big organ.
Yeah.
There will be some contrabassoon-y things. I bet there's less than 5 mainstream instruments that have anything approaching 20 hertz, right? What's the lowest note on a piano? Way above 20 hertz, isn't it?
Way above that.
You're like, there's not much down there. Electronic dance music generally is not hitting below 20 hertz ever.
You'll have regardless of any of this, you'll have an excellent experience. They're excellent subs. Right. You're going to have an excellent experience. And room gain will help depending on what's going on in your room. Stephen Kelly, something Bed said about Dolby and then expecting full range speakers in the past in an M-Wave room with JTR because JTR did this in 24. adding subwoofer on each speaker has me thinking, why aren't we aiming for full range now? And my answer to that is because typically where a speaker is placed is not necessarily the best location for a subwoofer.
Yeah. Watch last week. I explained in quite a good detail, I think, why I don't like this idea. When I'm using multiple subs, I'm generally using it to even out the response. If you're doing essentially stereo subs or making every channel full range, a lot of the benefits you get from multiple subs evening out the response, you would take back away again by not using them that way. It's not something I like or do myself.
But you know what? If I was selfish and it was all about me and there was only one important thing, that's what I'd do for my cinema.
For one single seat.
For one single seat. Everyone else is screwed.
And the reason it's different for Dolby is that in a commercial sized auditorium, they don't have small room problems.
No.
And they don't
room
have
makes a big difference. The room dominates the experience. Pime K, talking about boosting bass. My per listen subs have multiple profiles, THX boosting cut. Should I use boost if I use it with waveforming or stick with THX and boost more in the Trinov room?
Stick with THX and do it in the Trinov.
There you go. Let the Trinov be in. I would say you want one device to be in control as much as possible.
The per listen has a nice limit to it. Won't let you break it.
Yeah, that is true. Steve McGoley, can you remind us,
we've answered this? We answered this during the
cool. And then Brian Cobb, I have 6 PB17s and 2 Ascendo 32s, but only have 1 layer of sheetrock on the sidewalls and ceiling. How much would green glue and a second layer of sheetrock help?
A little, not much. Again, it depends what frequency you're talking about.
So if you're talking about getting down to infra, the wavelengths are so long, they don't care really about sheetrock.
Infra, it's going to make little difference.
Yeah.
60, 70, 80, it'll make a useful difference.
Sure. The other thing that it'll help.
So green glue
the other thing that it'll help.
Material.
Well, what I was going to say was exactly that. Is the other thing it'll help is potentially removing, you know, resonances and stuff in the room with like hearing the vibration of the sheetrock against studs, or it allows it to move a little bit because it never fully cures or dries.
So when we get this perfect room gain, we're going to need stiffness and density, and the green glue is intentionally introducing damping. So yes, the additional board is adding more density, well, it's adding more mass. The stiffness is actually slightly compromised by a damping material, so it would be better, but it's not a. There's compromises like everything else.
But you theoretically could get around that because you're going to be in the upper frequency ranges, and the subwoofer should be more capable, so it's not as much of an issue.
Sure,
theoretically. Okay, but anyway, I think that brings us to the end. I have to jump to a meeting. Do you guys have anything to say when we wrap this up?
I mean, this is a conversation that could just go on for days and days and days and days. It's really, really, really deep. My only advice to anyone is just try and understand the maths or whatever you want to call it. If you begin to understand the maths, if you begin to understand what happens at a boundary, what happens with room gain, the difference between sealed and ported, you understand system gain and system gain structure, you understand the equation that I'm going to send to Ryan, and put all of that together and demand really great data from your suppliers, then you're going to be in a fantastic position to make predictions and hopefully not make too many expensive mistakes.
Okay. Well, Peter, it's always great having you on. I'm sure we will do it again.
Pleasure.
And Ben, always great having you on. I know we will do it again.
We will.
Either this week or next. But
I think it'll be a week today.
Okay. So we're going to continue these conversations. I don't know when we'll continue this specific conversation because I don't want to monopolize Peter's time. But it is important that we really hammer this because I think it's an important topic. It's one that it's very easy to get wrong. And the more you can get this right, because bass, I think, is underutilized. Everybody wants to focus on the speakers, the things that are up in front. Subs aren't necessarily the prettiest thing in the world, but we derive a lot more of our experience from the subs than I think people realize. So the more we can properly implement them, the better. Peter, do you have something?
Just that when it comes to bass, there's so many common misconceptions. There's so much crap talked out there about what goes together. Just follow the science, follow the maths. You can never totally predict it, but you can get a lot closer.
Yep.
And this isn't about always needing to spend loads of money on a system and to always have infra subs and always have this, that, and the other. It's whatever your budget is, follow the maths, follow the engineering, and you're going to get the best value.
You got it. Well, guys, this is where we wrap it up. Thanks for joining us on this episode of the AV Experience. We'll have more of these. And like I said, we'll have Peter and Ben on continuing to go forward. If you guys have any questions, please drop them in comments. And if I don't have an answer, I will relay them to these two because they are much smarter than I. But enjoy your home theater journey. Stay safe out there, and we will see you guys